Hello students, let us start our today's session from the chapter Alcohols, Phenols and Ethers. Today we are going to see about ethers, in which we are going to learn about the classification of ether, nomenclature of ether and their preparation and properties. Now let us find first of all ethers. Ethers actually the general formula given ROR. Here we have the R group that might be a similar R group or even a different R group. In common name, the ethers are named as alkyl ether. Here if at all both of them are similar alkyl group, then it will be dialkyl ether. Or one will be the shortest chain, the other will be the longest chain. Then those both alkyl group will be called upon alphabetic order. Suppose ethyl, methyl, ether is there, we have to call first of all ethyl followed by methyl and ether. IUPAC nomenclature, ethers are named as alkoxyalkane. Here the alkyl part with the oxygen should always be the smaller alkyl part, or the length of the chain will be shortest length. For example, if I have this is a butyl group and this is a methyl group, then that makes methoxybutane. It never comes butoxymethane. So in IUPAC nomenclature, we have to consider the length of the carbon chain on either of the oxygen atom. But in common name, both the alkyl groups to be called based on their alphabetic order. Then what about that ethers? How do they classify? Ethers are very good solvents and they play vital role in most of the field as solvent. So ethers that can be classified into simple or symmetrical ether and mixed or unsymmetrical ether. This classification arises out of the alkyl group that is attached with the oxygen atom. If both alkyl group attached to oxygen are similar, then it is said to be simple ethers or symmetrical ethers. Or about the oxygen atom, if you find two different alkyl group or one alkyl and aryl group, then those are said to be mixed ether or unsymmetrical ether. So these ether, the unsymmetrical ether as well as the simple ether that may give rise to the isomerism of chain isomerism, position isomerism as well as metamerism. This and all we discussed in our hydrocarbon basic concepts of organic chemistry we discussed. Nomenclature. How ethers are named? Based on, just now we discussed alkyl ether, alkoxyalkane, common name is alkyl ether, IUPAC name is alkoxyalkane. So let us have these compounds in which the first member of the compound is methyl ether. So how many methyl group I have? This is one, this is one. So that makes its common name dimethyl ether. And its IUPAC name? Here the IUPAC name, the prefix goes alkoxy group. So always the alkoxy group becomes the prefix of hydrocarbon. So we have to take, this is both of them are similar alkyl group. So one of the oxygen that makes the prefix of IUPAC name. So we can say methoxy. Methane. So the prefix methoxy and the alkane, it has only one carbon, root word meth, it has no any unsaturation. So the suffix is ane and secondary suffix nothing is there. That's why the name is methoxymethane. If I have methyl, ethyl, one side the alkyl part is methyl, the other side the alkyl part is ethyl. So common name we have to say alphabetic order. So first of all ethyl followed by methyl. So we can write ethyl, methyl, ether. At the same time its IUPAC name. The shortest length of alkyl group should make a alkoxy group. So this becomes the alkoxy group as prefix. So methoxy, two carbon are there. So root word eth, the name is methoxyethane. And similarly, we can find the methyl propyl ether. Here the alphabetic order, meth followed by prop. So the name is methyl propyl ether. This when the oxygen has one of the alkyl group longer, that means more than 2 carbon, there we have to start the numbering. So I can start the numbering 1, 2, 3. So to the first carbon, the prefix methoxy group is present. So I can name this as 1-methoxypropane. So here the locant number of methoxy group to the first carbon of propyl. So the name is 1-methoxypropane. The next one. To the propyl group, I can write its isomer. So when I write the isomer, I will get isopropyl group. The alphabetic order, when we write, we are not supposed to give the terms iso, neo, tertiary, secondary and all should not be considered for its alphabetic order. So once again, name of the compound is methyl isopropyl ether. But its IUPAC name it goes, we have to start the numbering of the propane. So we can give this is first carbon, second carbon, third carbon. To the second carbon, methoxy group is present. So we can write along with its locant number. So the name it goes 2-methoxypropane. And then if I have the 4 carbon atom and one of the carbon methyl group to the side chain, I may find here 4 carbon and in which one iso structure is there. So the common name of the compound it becomes, this is butyl part, this is methyl part. So a common name it goes iso-butyl methyl ether. Alphabetic order, iso do not consider, only the butyl takes its alphabetic order. So we are writing iso-butyl methyl ethers. And its IUPAC name, once again start the numbering here, first carbon, second carbon, third carbon. So in this chain we have 2 methyl substituent and the functional group. So the name it goes methoxymethyl because meth. Oxygen prefer first, oxygen goes first later, why? That's why the position it comes 1-methoxy 2-methylpropane. So the IUPAC name it goes 1-methoxy 2-methylpropane. The next one, in the cycloalkane we have alcohol as well as ether, where the ether it goes prefix, alcohol it goes suffix. But when you compare the priority of these functional group, alcohol takes the priority. So the name of the compound is cyclohexanol, to which the alkoxy group is present as the substituent. So with respect to the first group alcohol, methoxy at the second position. So its prefix is 2-methoxy and it is a closed structure. For this the cyclo prefix is given. So the name prefix is 2-methoxycyclo. How many carbon are there? 6 carbon. So hex. All of them are saturated. So N. 2-methoxycyclohexane in which the OH is present, so that it takes the suffix and hence the name becomes 2-methoxycyclohexanol, where alcohol is present at the first position. So we can write this is as 1-alcohol. So the name it goes hexane 1-al. In this case, the prefix of the compound is methoxy and it is attached with the benzene group. So the prefix methoxy, benzene. So the name is methoxybenzene. And anisole is the name which is considered as both common name as well as IUPAC name. So let us take methoxybenzene as anisole itself. So that's all. The classification and nomenclature of ethers. In the nomenclature of ether, for IUPAC name, you have to find the alkoxy part should bear lesser number of carbon atom and that alkoxy group should find the position if at all the other alkyl part is the longest chain. And in that longest chain, if you find any other substituent, that has to be taken as the prefix or the suffix based on the nature of substituent. and in common name we have to write alkyl ether only. So both R group you have to find the length and then you have to identify their alphabetic order. Based on that you have to say the alphabetic order for their common name. Preparation of ethers. Ethers that can be prepared by dehydration of alcohol, one method. And another method, Williamson's ether synthesis, and the third method from diazomethane. So let us find first of all dehydration of alcohol. This dehydration of alcohol that follows SN2 reaction. And here both the two molecules of alcohol that undergoes intermolecular dehydration at 413 Kelvin in presence of acid. So that forms ether, and this method is preferred only for ethers having primary alkyl group. This method is suitable for the preparation of alkyl groups must be primary. Why? Because the dehydration of alcohol that can take place at two different temperatures, one at 443 Kelvin and other at 413 Kelvin. At 443 Kelvin, we prepared alkene from alcohol, and that follows intramolecular dehydration reaction. So at high temperature, alcohol preferred to over elimination reaction rather substitution reaction. But at low temperature, the substitution reaction competes over elimination. So in this substitution, where the alkoxy group behaves as the nucleophile of the reaction. So we need to take at least 2 units of alcohol we require, one out of which behaves as alkoxy group, that is the nucleophile, and other one that behaves as alkyl group. So this behaves as a carbocation or the substrate. This alkyl group we can make it as a substrate. So the dehydration of alcohol, in the preparation of ethers we have to take 2 units of alcohol and both must be primary. Okay, if at all secondary or tertiary alkyl groups are there, what will happen? See, this dehydration of alcohol that follows SN2 mechanism. SN2 mechanism is suitable and fastest only in case of primary alkyl primary compounds only. But in the case of secondary or tertiary alkyl group, then that will follow the formation of intermediates carbocation, and those carbocations are more stable than that of primary carbocation. And the next thing, secondary and tertiary alkyl groups are usually bulky in nature compared to primary alkyl group. So such bulky group that may hinder the approach of alkoxy group to the substitution, and hence the elimination will follow rather substitution. So in case of the alkyl group being secondary or tertiary, then that will follow SN1 mechanism through the formation of intermediate carbocation, secondary or tertiary, and those carbocations are more stable and hence the elimination reaction competes over the substitution, so we will get an alkene. So the temperature is the one that decides whether elimination follows or substitution follows. At high temperature, elimination that follows to form an alkene. At low temperature, substitution follows to form an ether. So let us discuss about the mechanism of dehydration of alcohol. And here the dehydration of alcohol takes place between the two molecules of alcohol, and hence it is said to be intermolecular dehydration. But within the molecule, if at all the dehydration takes place, then it is said to be intramolecular dehydration. Mechanism of dehydration of alcohol. So dehydration of alcohol at 413 Kelvin, where substitution competes over elimination, and the alkyl part of alcohol should be primary. So let us explain about the mechanism of formation of ethoxyethane. So the first step is, this is the dehydration reaction follows in presence of acid. So this is acid catalyzed dehydration reaction. So the first step is alcohol gets protonated due to the presence of acid catalyst sulfuric acid. And in alcohol we may find there are two lone pairs of electron over the oxygen atom, so that can abstract the proton from the sulfuric acid. So we will get protonated alcohol. And to this, the other molecule of ethanol that behaves as nucleophile, a neutral molecule, since oxygen carries the lone pair electron. So this nucleophile that attacks, as the water molecule withdraws the electron from the carbon, then the nucleophile attacks the carbon. So this is electrophilic site to which the nucleophile attack, because the oxygen won't be stable with the positive charge. So it removes its shared pair of electron from carbon atom. So we are getting minus H2O, and the nucleophile subsequently attack that CH2 carbon, because when it removes that, develops a positive charge over here. To the positive charge the nucleophile attacks. So in this case, once again oxygen acid donates electron to CH2, oxygen carries the positive charge. So the oxygen that withdraws the electron from the hydrogen, that makes its proton, so minus H plus it forms. So diethyl ether is formed. So this can be explained in 3 steps. The first step, what we said, protonation of alcohol. See, protonation of alcohol, that forms protonated alcohol. That means oxygen of that OH group that attract the proton from the acid. So we are getting protonated alcohol. Then to which what we explained, attack of nucleophile and subsequent elimination of water. So here oxygen bears the positive charge, so it withdraws the electron from carbon, and hence the alcohol that attack this CH2 group. So we are getting protonated ether, from which the proton gets eliminated as it bears oxygen positive. So hydrogen, it withdraws the electron from hydrogen, so it makes ether plus H plus. So this is the single step reaction, because SN2 reaction follows in single step. The single step is explained in 3 different steps. But in the case of alcohol as secondary or tertiary, we do not get ether. Instead, we will get alkene, because as soon as the elimination of water takes place, that makes the carbocation. Here we have a primary carbocation. That primary carbocation is highly unstable. But in the case of secondary or tertiary, carbocation will be stable, and hence they lead to elimination rather substitution. The next most important method of preparation of ether is Williamson's ether synthesis. It is a name reaction. Actually, this is also nucleophilic substitution reactions. And from this method, we can able to prepare aliphatic ethers as well as aromatic ethers. But whatever it is, as the reaction that proceeds SN2 reaction, it involves an alkyl halide and an alkoxide. That RONA is alkoxide. The alkoxide, that is a base, and the alkyl halide is a substrate for the reaction. So this base that behaves as a nucleophile for the reaction, and hence it proceeds nucleophilic substitution reaction. So we know RO minus Na plus, this is sodium alkoxide. When the halogen, most electronegative, that withdraws the electron from alkyl group, subsequently the alkoxy group that attacks the R, and hence we are getting ROR plus NaX. So ether is formed. So as the halide withdraws its electron from alkyl group, that may attack this Na group. So we are getting NaX. And as the removal of halide ion that develops a positive charge over the alkyl group, and hence the base that attacks the electrophilic site, we are getting ether. This is what the reaction that follows in Williamson synthesis. And I already said it is SN2. And the base that could be a primary, secondary or even tertiary because it is a nucleophile only. But alkyl halide, it always be primary alkyl halide as a substrate. Why? Because alkyl halide only develops the carbocation. The primary carbocations are highly unstable and the smallest group. So the smallest carbocation that do not hinder, though the alkoxide ion is a bulkier one, and hence it finds ease of the reaction. But in the case of alkyl halide is a tertiary one. What will happen? We may find here. See, this is sodium ethoxide. It is a primary compound and it is also a nucleophile because alkoxide I have. And in this case, we have taken tertiary butyl bromide. We know well the halogen that withdraws the electron. So when it withdraws the electron, it develops a positive charge over the carbon atom that makes this as tertiary carbocation. When tertiary carbocation is there in presence of a strong base and bulky base, what happens? Elimination competes over. So one of the hydrogen from this alkyl group that again moves towards the carbocation and this nucleophile CH3O minus that abstract the proton from the alkyl group. So we are getting CH3, C double bond CH2 CH3 plus NABR plus CH3O with the hydrogen alcohol. If the alkyl halide is tertiary one, then we are getting an alkene as the product and the base is into alcohol. So in Williamson ether synthesis, we should always consider the substrate will be primary alkyl halide. But the alkoxide could be a primary, secondary or even tertiary. No issues, that will follow SN2 reaction. If it is reversed, we do not get ether. Instead, we will get an alkene and alcohol. When we have CH3Br, we can say the Br the most electronegative that withdraws the electron from methyl part. And here the product is tertiary butoxide. This is tertiary butoxide, a bulkier nucleophile, and we have tertiary butoxide ion and sodium ion. So the halogen that adds with the sodium, so we are getting NABR. As it develops a positive charge over the methyl, this butoxide ion that attacks this carbon, and hence we are getting tertiary butyl methyl ether, or its IUPAC name will be 1, 2, 3 to the second carbon methoxy to the second carbon methyl. So the name is 2-methoxy, 2-methyl propane. So here we have taken the tertiary butoxide as a nucleophile. Instead of tertiary butoxide, we can take either CH3ONA or isopropyl alkoxide, that could also be taken. So this is how the reaction that proceeds depends on the nature of alkyl halide and alkoxide. Preparation of anisole by Williamson's ether synthesis. Just like aliphatic ethers, we can prepare anisole. In aliphatic ether, we discussed that alkyl halide should always be primary and the alkoxide could be primary, secondary or even tertiary. But in the case of anisole preparation, we need a base and we need a electrophile. So when I have sodium phenoxide with methyl bromide, I may find this phenoxide ion that behaves as nucleophile. And in methyl bromide, here the methyl group that behaves as electrophile. We know very well the ring that may facilitate electrophilic substitution, but it does not favor the nucleophilic substitution. So the alkyl halide should always be electrophile. So in this phenoxide ion, we may find the O minus that attacks CH3, whereby the Br with the sodium that makes sodium bromide with anisole. Suppose if you reverse, instead of sodium phenoxide, let us take bromobenzene, and the CH3Br is taken as nucleophile. So here it is the nucleophile. And what about the ring? See, the ring itself a strong nucleophile. Why? The halogen attached to sp2 carbon. And moreover, due to sp2 carbon is more electronegative. And the halogen that carries the electrons that may share with delocalized with the benzene ring, or it is in conjugation with the benzene ring, that develops a partial double bond between the ring and the halogen. So what happens then? Because of the partial double bond, it cannot be easily broken and the nucleophilic substitution cannot be facilitated. So in Williamson synthesis, in the preparation of anisole, we are not supposed to take an aryl halide with alkoxide. Always the aryl group should be a phenoxide ion to which it may undergo electrophilic substitution. So we may get anisole or it is methoxybenzene. But the reverse is not true because of the possible reasons of the formation of partial double bond and the high electronegativity of sp2 carbon and the possible repulsion of the benzene ring with the nucleophile. The next method of preparation of ether is from diazomethane. This is diazomethane because it has two nitrogen atom. The azo, it represents nitrogen. Two nitrogen are there, so it is diazo. One carbon is there, methane. So when ethanol is boiled with diazomethane in presence of hydrofluoroboric acid, we will get methoxyethane, in which the nitrogen is expelled as the gas. Properties of ether. Let us discuss about the physical properties of ether. Ethers are usually volatile liquids. They can easily evaporate even at room temperature. That's why it is said to be a volatile liquid. And it possesses the weak polarity, and hence the boiling point of ether is higher than hydrocarbon but lower than alcohol. What is polarity? Polarity is as a result of the dipole moment of ether. See, oxygen is bonded with the two methyl group and both of them can donate its electron towards the oxygen. So the movement of electron towards oxygen is given to the same direction. And the oxygen carries the lone pair electron that also can move in same direction. And hence the resultant dipole moment of ether is greater than 0, that makes the molecule becomes polar. So because of the resultant dipole moment which is greater than 0, that renders polarity to the ether. But the polarity of ether compared to alcohol is smaller, and hence the boiling point of ether is smaller than alcohol but higher than hydrocarbon of same molecular mass. Solubility. Oxygen is present in ether, and oxygen that carries a lone pair of electron as well as more electronegative atom. So this is the reason it makes to miscible with the water, but only the lower member of ether miscible with the water. But when size of alkyl group increases, that do not dissolve in water because of the hydrophobic nature of bulky alkyl group. So oxygen atom of ether that can make hydrogen bond with water, so that facilitates the miscibility of ether in water. Chemical properties of ether. Let us find the reaction of ethers with hydrogen iodide. Ether that can react with hydrogen iodide in two different ways, one with the equivalent of Hi, the other one with excess of Hi. The equivalent of Hi means both ether and hydrogen iodide are in same quantity. For example, we can say this is 1 mole, this is also 1 mole. So when both of them are in same quantity, then we may find there is a formation of alcohol and alkyl halide. Because oxygen carries the lone pair electron, so that it can attract that proton of hydrogen iodide. Subsequently, the nucleophile I minus attack the other alkyl group. So we are getting alcohol and alkyl halide. But in the case of excess of hydrogen iodide, the same step it proceeds. First of all, that forms one alcohol and one alkyl halide. And this alcohol is another nucleophile. So that may react with the second mole of hydrogen iodide, where the OH that with the hydrogen makes water and I minus that attract that R plus group. So it forms alkyl halide. So when you add these two reactions, you may find the ROH can be cancelled. So how many times I have ether? ROR. Plus how many times HI are there? 2 times. So 2 HI, that gives 2 times of alkyl halide 2 RI plus a molecule of water. So with the equivalent of HI, we may expect alcohol and alkyl halide, but in excess of hydrogen iodide, we will get 2 moles of alkyl halide with water. Okay. Then the question is, out of the 2 alkyl group, which one will prefer to go with the hydrogen and which one will prefer to add with iodide? That can be explained based on SN1 and SN2 reaction, because this follows substitution only. So when SN2 we consider, we know well that alkyl group must be a primary alkyl. So let us take methoxyethane. Here when both R groups are same, then there is no difference. Either of the alkyl group can go with the hydrogen and halide. But when 2 different alkyl groups are there only we have to find, depends on the mechanism of reaction. Let us proceed. Methoxyethane. So here the oxygen, it carries a lone pair electron and hence it abstracts the proton from hydrogen iodide. So it forms protonated ether, and to which the nucleophilic attack takes place, where the nucleophile is a bulkier, so it finds the smallest alkyl group among the ether and hence it abstract that can substitute with methyl group. So the alcohol, the OH group withdraws the electron from carbon, where the I minus attacks that electrophile of CH3. So we are getting CH3I and ethanol. So when 2 alkyl groups are similar, no issue, we will get one alcohol, one alkyl halide. But when 2 different alkyl groups are there, we have to find whether they are primary or not. If they are primary, the simplest alkyl group that adds with the bulky halide ion and the bulky alkyl group that goes as alcohol. So we are getting alcohol and alkyl halide. Suppose if one of the alkyl group is tertiary, the other alkyl group is primary. Once again, let us proceed the reaction up to the formation of protonated ether. Now, you have a tertiary carbon and a primary carbon. We know well the tertiary carbon is more stable than primary carbon. So, the cleavage, where does it take place? Whether carbon, oxygen or O and methyl group. Actually, it takes place between tertiary carbon with the oxygen, because it develops a positive charge over the more stable carbocation. And hence, we are having methanol and the I minus attack that a tertiary carbocation form tertiary butyl iodide. So we are getting tertiary halide with alcohol. So you may find the reverse. Here the bulky group, the long chain goes alcohol. Here the smallest chain that makes alcohol and the bulky group that makes a halide. So when 2 different alkyl halide, particularly tertiary or secondary are there, we have to follow the SN1 reaction. Let us find it in anisole. anisole is methoxybenzene. So here the same procedure follows. First stage, the protonation of ether. So we are getting protonated anisole. The nucleophile has to proceed whether to break the carbon-oxygen bond of benzene ring or carbon-oxygen bond of methyl group. See, here the oxygen is bonded with sp2 carbon in a ring, but oxygen is bonded with the sp3 carbon in another side. So the side chain of alkyl is sp3 and that ring of oxygen with the carbon is sp2. We know sp2 carbon more electronegative and that could able to resonance stabilization, and the bond also much stronger. Because of the strong bond, nucleophile could not able to break, but it can easily break that weaker bond of alkyl and oxygen. So we are hitting alkyl halide and phenol. So in case of anisole, the bond breaking should be taken place between alkyl and oxygen, that is the side chain with the oxygen. Never the bond breaks between sp2 carbon with the oxygen because of its the strongness. So that's all the reaction with HI. Okay, here we have taken HI, but we have the compounds of HBr, HI, HCl. So what about the reactivity of hydrogen halide towards ether? The hydrogen halide is HX. How does it react with, and what about its reactivity? See, hydrogen iodide more reactive than HBr, which is than HCl. Once again, due to the bulky size of iodide, the reactivity towards ether is given in the order of HI greater than HBr greater than HCl. Some other chemical properties of ether. Ether may undergo auto-oxidation, but the process is very slow process. So during oxidation, the oxidation may take place either at the CH2 alkyl group or in oxygen. So when the oxygen, that is ether undergoes auto-oxidation, they may form diethyl peroxide. Or oxidation takes part in ethyl group, we will get diethyl hydroperoxide. OH will be formed, but the process is very slow. Auto-oxidation, the oxidation occurs on its own. So it takes place during the time of on standing. See, the other reactions of ether, it may undergo substitution reaction with the halogen in presence of light. So in presence of light, that makes the halogen is being substituted in alkyl part. So free radical substitution, and hence all the 10 hydrogen atoms of ether can be replaced by the chlorine. So we are getting perchloroether. And here we have 10 chlorine and 10 hydrogen removed. So we are getting 10 HCl. So we have to take 10 times of Cl2. Phosphorus pentachloride. Usual, the bond can be broken like this. So POCl3 and 2 molecules of ethyl chloride will be formed. Thionyl chloride, same thing. The bond breaks between the two alkyl and oxygen. So we are getting 2 molecules of ethyl chloride and SO with the oxygen SO2. Hydrolysis. This is formed during the intermolecular dehydration of alcohol. So when it is hydrolyzed, the water that can split carbon-oxygen bond and it can share like this. So we are getting ethanol as well as ethanol. 2 molecules of ethanol will be formed. And with the acid chloride in presence of anhydrous zinc chloride, the bond it breaks either between any one of the carbon oxygen we may find here. So this makes negative, this makes positive. So in which the Cl will attack this. So we are getting CH3, CH2, Cl. And this is the acyl part CO that attacks that O minus. So we are getting CH3, COO, CH2, CH3. So ester is formed. So that's all the properties of ether, in which the aliphatic ether undergoes reaction with the hydrogen iodide, auto-oxidation, as well as it shows its reaction with chlorine, pentachloride, thionyl chloride, water and acid halide. Now let us see the reaction due to benzene ring in anisole. So let us see the chemical properties of anisole, in which the electrophilic substitution reactions takes place in benzene ring. So in anisole, In anisole, the oxygen carries the lone pair electron, so it is in conjugation with the benzene ring. So when it moves, you may find the presence of negative charges at 2, 4 and 6 position. So the anisole, in anisole, the methoxy group is orthopara directing group. So we may find this electron in it goes inside the ring and the electron goes to the pi electron comes to 4th position and hence this enter into that and this comes out. So we are getting that 2, 4, 6 position of negative charges and hence the methoxy group is said to be orthopara directing group. But this is not that much activating towards the electrophilic substitution reaction compared to OH, because in OH the hydrogen is there. This hydrogen neither plus I group nor minus I group, but in methoxy CH3 is plus I group. What it will do? It may increase the electron density of oxygen by giving its electron and hence the OCH3 group is not that much activating the benzene ring just like alcohol. So let us find nitration reaction. When anisole is nitrated in presence of the nitrating mixture sulfuric acid and concentrated nitric acid, we are getting orthonitro-anisole and para-nitro-anisole, where the para is the major, the ortho will also be minor. And in halogenation reaction, the halogen is taken in presence of ethanoic acid, that is CH3COOH. This will also undergo either in for second position or in fourth position. So there also we may find the formation of 2-bromo-anisole and 4-bromo-anisole. In Friedel-Crafts alkylation reaction, where alkyl halide in presence of anhydrous aluminium chloride, this forms 2-methoxytoluene or 4-methoxytoluene. This is 2-methoxy, this is 4-methoxytoluene. And in acylation, acid halide with the anhydrous aluminium chloride, we are getting 2-methoxyacetophenone and 4-methoxyacetophenone. A ketone derivative is formed. That's all the electrophilic substitution reactions in anisole. Okay students, that's all the chapter. Here we have completed alcohols, phenols and ethers, their preparation properties, nomenclature, structure, everything. Hoping that you will understand all the concepts very well. If you have any doubts, you please post me in comments. I am here to clarify everything. Okay, let us see our next class with the new chapter and with the new topics. Until then, bye bye.